Okay, today we're going to discuss the life cycle of medium voltage switchgear, particularly modern vacuum gear. The thing that we all have to realize is the majority of the switchgear that we deal with, and we're from that industry. I see the list of some 300 participants today, between 300 and 400, and the majority of you are involved in the electrical industry, the switchgear testing, construction, manufacturing, engineering, all those different sides. And I'm going to target a modern vacuum gear. And the reason I pick it out is because sometime in the 70s, early 80s, it became the standard by which the infrastructure here in the US is supported by. Previous to that, you saw air breakers, switch and fuse, oil breakers. Even in the early 80s, a few gas breakers made it here from Europe, but didn't really get a good footprint. And sometime in the late 70s, early 80s, the vacuum technology became kind of the leader and the clear-cut favorite. And through my career, I have seen many ideas put forward for technologies to replace vacuum. First, obviously, it was SF6 or gas breakers. That did not work because of a lot of issues. They're fairly complex. You have the gas issue, you have pressure seals, pressure transmitters that create leaks, and then you have the environmental concerns. So a lot of things stacked up against gas. Actually, gas was a good idea and an excellent way to go about this problem. But vacuum through all this has kind of become the standard. When I got into this business about 300 years ago, air technology was primarily what was seen in the industrial and utility market in the United States. And air breakers are fairly complicated. They have big, heavy mechanisms that have to move a lot of mass. They require a lot of cleaning, a lot of carbon buildup, arc contacts, intermediate contacts, main contacts. Some of them have 30 or 40 springs per pole. So they're very complex and they're very easy to be affected by thermal loads, repetitive applications, any of that sort of thing. Where I was at was that, air technology is fairly complex. You have to move a lot of mass, a lot of distance. So you have to have a big, tough mechanism. You have to have a lot of springs, age, time, heat, effect springs. So everything was working against the air breaker in comparison to the vacuum breaker. The vacuum breaker moves a very small amount of mass, a very small distance. So the mechanism can be very light. So there's not as many springs, there's not as much energy, as much WK squared involved. So consequently, you don't do as much damage to the breaker every time you open and close it in repetitive applications. Where an air breaker, if you get an air breaker, a 15 kV or 5 kV heavy current, heavy MVA air breaker into a repetitive duty application, you just beat it to death because you're dealing with 1,000, 12, 1,500 foot-pounds of force. And you're jamming it together. There is sometimes a biospring involved, or there is some cushioning, but still you just beat the contacts to death. Consequently, you have to take it apart fairly often and burnish the contacts, clean the contacts. You have to out of the arc chutes. Moisture is a big deal. Airborne contamination is a big deal. Spider webs, dirt, carbon black, titanium pigment, iron ore, whatever's in the air is a big deal. But with a vacuum breaker, at least the interrupting part of it is sealed in a canister in a container, so it's somewhat isolated, and it takes very little energy. So vacuum kind of pushed aside the air breakers. A lot of that was economic because the hours that it took to maintain the old air breakers obviously cost the plants a lot of money. When I got into this business about 300 years ago, the maintenance departments in these large plants and utilities pretty much did all the work themselves. So they had either trades, unions, or mechanics and electricians that took care of this equipment, and they had their own shops. and they spent a tremendous amount of time, and most of that expertise is gone today. So consequently, the advent and the implementation of the vacuum breaker was a very good thing, because what it enabled us to do was to not miss those shops quite as bad as if we'd have kept the air breakers. The economic side was essentially they were told that if they converted to this vacuum technology, these vacuum breakers, they wouldn't have to do as much maintenance. So the expense would be much less. So the vacuum gear would actually pay for itself over time. So today, when this gear goes into service, we're going to talk about its life cycle. And that's what the presentation today is about, is the 100-year optimization of this vacuum switchgear. Now, a lot of people, this 100-year thing scares, but if you think about it, the majority of that infrastructure went in the early 80s, late 70s, early 80s. So it's already 40 or 50 years old today. So we're halfway there right now. And I don't know if anyone out there knows what the next big thing is going to be, what the next replacement breaker for the vacuum breaker is going to be, but the solid state breaker, the nano and graphene technology, all the things we've been promised over the last years has not worked out. So there really is not a really good, close to market alternative to the vacuum circuit breaker at the higher power levels. Now, sure, you can turn a solid state circuit on and off at a few thousand volts and a few thousand amps. But when we start talking about the newer breakers rated 50, 60, 70, even 80,000 amps interrupting ability, I think we're a long ways away from that with solid state technology. Consequently, I think we're stuck with the vacuum breaker. That's a good thing. It's done a good job. It's going to continue to do a good job for us. And we're stuck with this technology for another 40 or 50 years. The reason being is, how do we go in and remove that gear without disturbing the cables? With all the build out that's been done around the switchgear, bus ducts, armor cable, steam pipes, whatever, it'd be nearly impossible to get to the gear to replace it. So really, we're kind of stuck with upgrade, life extension, and those sorts of things that we're going to talk about today and through these next 3 segments. So the next 3 segments obviously will be more technical than what we're going to deal with today. Today, we're going to talk about the life cycle. And here's kind of the big picture. So here's the roadway to 100 years, so to speak. And today we're somewhere in the middle. That little truck there is us. We're moving along. And to the left, you see the equipment was manufactured. Then you see that's primary cycle, where it's used for about 25 years and maintained for about 25 years. And that's pretty much the life cycle that we've been pitched for the switchgear. When GE, bless their heart, even though they're gone today, hello to all my ABB friends out there today, came around and pitched this, when Westinghouse come around and pitched this, when Alice Chalmers, Brown Boveri, all these people came around and pitched this years ago. Basically, they promised us a 20 to 25 year life cycle on this switchgear, and it's done a great job. It's far exceeded that. It has twice exceeded what it was designed to do. And then you see the secondary cycle, which is another 26 to 50 years. And that's where we're at today with most gear. Most gear is over 25 years old, somewhere between 25 and 50 years old. Then you see these life extension segments, primary and secondary life cycles. That's really where you start to double and triple the proposed life of the equipment. And we have all kinds of things available to us to do that today. Converting insulation, converting controls, doing all sorts of things to bring the equipment up to where it will live longer. And we're going to talk about that a little bit today. And we're going to zoom in and talk about it in great detail in the next 3 segments. So this is the life cycle, essentially the big picture. You've got when the equipment is manufactured, its primary cycle, its secondary cycle, its primary life extension cycle, and its secondary life extension cycle. And this paper that I've got in my hand describes everything we're going to talk about in better detail, and it'll be available at NETA. And this is a small excerpt from my 4-hour workshop that I'll have at NETA next month. So for any of you that'll be there, you'll be hearing some of this again, but I'm not going to get into the nitty gritty where I'm not going to ruin the good part for you. We're going to have a few icons today to discuss. When we look at our roadmap here, there's going to be some icons. We're going to deal with functional testing, electrical testing, the general maintenance, inspection, putting human eyes on equipment, cleaning, lubricating, adjusting, all sorts of electrical testing, various controls. Is equipment energized or de-energized? These are the icons you're going to see through this presentation. And just to give you an idea of what we're talking about, obviously these little eyeballs here is a human actually doing an inspection, because there's no way you can get away from that. That's really the best thing we can do for this equipment is operate it, clean it, and put human eyes on it. You can't always do that. You can't always get to the equipment. You can't always get it out when you want to. Lots of times operating conditions in hospitals and data centers and lots of facilities won't won't allow you to get the equipment out on regular intervals. We're also going to talk about intervals. And then we're going to talk about lubrication, and we're going to talk about cleaning, just plain cleaning, exercising, cleaning, inspecting, and lubricating, and how important that is to these mechanical marvels we call circuit breakers. And these circuit breakers fit into a panel that we call switchgear. Okay, so I've done this. Some of y'all seen this before, but if you take and you press your hands together, really hard. So this is the moving contact. This is the stationary contact in a vacuum breaker or an air breaker, whatever kind of breaker you've got. And you push them together, the circuit is closed. So the circuit is energized and it's possibly it's passing power through the breaker. And then when you do this, it opens and then it breaks the contact, and then current stops to flow. Potential is no longer applied across the contacts. Essentially on, off, on, off. Pretty simple, right? Just like a valve. The difference is with a circuit breaker, I'm a big guy. I'm a 230-pound guy. You take and you push your hands together really hard. Okay, you have a hard time putting 1,200 foot-pounds together with your hands, but if you push as hard as you can, you put 40, 50, 60, 80, 100 pounds of pressure. Now you hold that 5 years, and then you open. So what you're asking a circuit breaker to do, and what you're asking your lubrication to do, is to push the contacts together with 1,000 pounds of force, hold it for 5 years, 3 years, 7 years. But then when it's called upon to act, you want it to act as if it was only 1 day old. So that's what you're asking your mechanism to do. That's what you're asking your lubrication to do. And lubrication is one of the real keys here, because lubrication, time, heat, chemical reaction, airborne contaminants are all the nemesis of lubrication. So quite often you'll see interrupting times and parting times that will go up proportionally with time. So there's been studies done over what the correct maintenance cycle might be. And for the purpose of this presentation, I've selected 5 years. I personally don't believe in 5 years for all applications. I think 3 is kind of a sweet spot. But it depends on your situation, how dirty, how clean is the environment, is it distribution, is it repetitive duty, how critical is the circuit? All these things come into play, and we'll discuss them in detail when we get into the various types of maintenance strategies in our next sessions. One of them will be geared toward acceptance testing, one towards maintenance testing. And both of those kind of have a different strategy when it comes to testing and maintenance and inspection. So just always remember, lubrication is a key, putting human eyes and keeping everything clean. It's the least you can do. So now we're going to move on. Now we're getting to the original equipment's being manufactured stage. Wow. So here we go. We're taking these raw materials, we're digging them out of the ground, or we're taking material and we're melting it down and recycling it, which is substantially more energy efficient. And we're building a copper plate, copper bar, copper wire, steel, iron, polymers, plastics, ceramics, things that come out of the oil, things that come out of the ground, all the raw materials that go into a piece of switchgear. So these are manufactured after they're drawn out of the ground, drawn out of the environment, and they go into the big assembly plant. So in the big assembly plant, these raw materials go into building switchgear. So at the plant, you have all these sub-suppliers that build all these components. They're shipped into the plant, then they're assembled into switchgear. The switchgear is the enclosure. It's got these draw-out drawers that essentially the breakers fit into, and the breakers connect through primaries. Okay, they connect through primaries into the cell. This is one of our breakers. This is one of our replacement breakers, for instance, that would plug into a piece of switchgear. Now, the breakers are also assembled in a breaker assembly plant, which sometimes is part of the same plant. Sometimes they're assembled down the street or in a sub-supplier and then shipped into the switchgear plant. The switchgear is assembled, instrument transformers, current transformers, wiring can be very complex, possibly generator or transfer gear, or it can be very simple distribution gear. And then you see a little logo here. You've got a guy doing all kinds of inspections. You've got a certain amount of electrical testing. They'll push current through the control circuits. They'll push current through the trip circuits. They'll finger the protective devices. They'll open and close the breakers. They'll push three-phase current and make sure all the metering indication and all the relaying works. They have tests for all this at the plant. So the switchgear is tested pretty thoroughly. The breakers are tested, normally open and closed about 300 times before you see them. If you ever look at the counter on a breaker, quite often the counter on the breaker will say 9,996 or 9,992. That's because it came into the plant several hundred clicks before zero, and they intend to put enough operations on it to get it back to zero, but quite often they don't. So the equipment is manufactured. There's a certain amount of batch and quality assurance testing that goes on in the plants. And believe me, they all try to build a quality product. They all try to build a quality product. And I can get into all sorts of problems and things we've seen with new gear. That's there again for another session in the ATS session. But let's just understand that they're trying to build a quality piece of equipment. Let's assume it is. We see about 12% of the new equipment that we see in the field and in our plant, new breakers that came in, that there's some kind of problem with. 12%. Okay, when it comes out of the factory, excuse me, I get a little dry because I'm talking a lot. When it comes out of the factory, obviously, if it fails these tests, some things are scrapped. There's a little scrap pile, and then sometimes a guy gets it and repairs it and it comes back. That's called a first pass testing. So sometimes some things that fail can't be repaired. Let's say a piece of insulation fails, a piece of epoxy or composite insulation fails. Well, it's pulled out and scrapped. Let's say a vacuum interrupter has a high leak rate and it fails. Let's say there's all sorts of things that can fail in this testing process, and it's replaced with a new component, okay? Because their first time pass rate's not 100%, nor is any type of switchgear, any type of manufacturing. Then the good equipment takes the other path and gets sent on this truck and gets sent out to the user. So that's coming toward you. It's coming toward you or your customer, and it's on that truck and it's headed out. There's the switchgear and there's the breakers. It's loaded on the truck and it's headed to you. So now it's through the equipment's original manufacturing process, and we're into your operational primary cycle, which we're going to say is 25 years. We're also going to say that your particular maintenance cycle is every 5 years, that every 5 years, you're going to pull the equipment out of service and do some testing inspection. What are those tests? What are those inspections? There again, that's the next segment. But let's just say that you have a maintenance program that you adhere to for acceptance testing this new gear. You have some sort of person, a third party or the original manufacturer or Joe down in QA. You've got somebody that's going to inspect this gear. This looks complicated, doesn't it? This is actually the primary life cycle path for your switchgear and your circuit breakers. And we're going to break this down into sections to make it easier to understand. But basically, the gear comes to the plant there on the right top in a truck, gets unloaded, and it works its way through this dangerous web to survive, kind of like an obstacle course. The first thing is it arrives at the plant. When it first arrives there, it often goes into storage. So quite often this equipment will go into storage in a warehouse, hopefully in a heated warehouse, hopefully covered and enclosed, but I've seen it stored outside with tarps on it. I've seen it frozen in warehouses with high humidity. I've seen all sorts of horror stories. So hopefully, let's say that it's stored properly with heat on it and it's not stored very long. I've seen this equipment in storage for many years before it's installed. I've also seen it come directly to the plant and go directly onto the pad off of the truck from the manufacturer and be installed and energized in a few days. So this does affect the warranty, okay? Most manufacturers' warranty is at, say, a year. Some are now giving 2 years. Some will give you 5 years if you let them do the acceptance testing. I'm not so sure that's a great idea, but some of the manufacturers today will give you a 5-year warranty on your switchgear if you let them do the acceptance testing. That doesn't make much sense, does it? Anyway, the general warranty is a year, and sometimes it's 18 months or a year after installation. So look very closely at what your actual warranty is, because you can set it in a warehouse with no heat on it, outlive the warranty before you install it, and do substantial damage to the equipment, degrade it substantially if it's not handled correctly and stored correctly. So always watch that and try to figure out where year 0 is. Where does your warranty actually start? Is it going to start in 5 years and 3 years and 1 year after installation? You need to know that from the plant level. At some point, the new equipment is pulled out of the warehouse, or if it's dropped from the truck directly onto the pad and it's assembled together. So the sections are assembled together. There's cross wiring, there's cross busing. The cable has to be connected. The cables have to be tested. The terminations have to be done correctly. The terminations have to be tested. There's a tremendous amount of that has to go on, but the switchgear is installed in your plant and the breakers are installed in the switchgear at some point. And there is some testing that goes on with that. Typically, that's what we call acceptance testing. And that's the next segment where we'll go into that deep, but but we'll briefly talk about it here where we just say that is where the equipment is tested to make sure that you got your money's worth. You got equipment that will do the job, will operate as specified, as the manufacturer said it would. And that acceptance testing can be done by a NETA certified, qualified, full accredited member of NETA. It can be done by a non-NETA company to NETA standards. It can be done by a non-NETA qualified quality individual. It can be done by the original manufacturer. It can be done by representatives of the contractor. And as an owner, that's to you to decide who you want to use. I can assure you there are quality, resourceful individuals in every one of those segments that'll do a good job for you. Basically, you find a lot of failures. You find a lot of issues in this particular point. When the switchgear comes together with the breakers, you open and close, test the interlocks, look at the rejection mechanisms, look at the MOCs, the TOCs, the controls, all the CTs are jumpers, all the jumpers are correct, all the bus joints are correct. There is a lot of diligence that needs to be conducted, because if you do a good job in acceptance testing, obviously the chance of your switchgear living a long and fruitful life is much greater. Some of this stuff will be returned to the manufacturer, or the manufacturer will be contacted and say, hey, we've got a problem, and they'll send their factory service people out. Quite often, that's a third party that's calling out those deficiencies. So as the owner or as the contractor, you have to get in between that and referee that. That can be a little tough at times. But there is a path by which, if this does not pass acceptance testing, there is some give and take there. So you have to determine, do you use an OEM? Do you use an independent? What's the good and bads of both? And we'll discuss that in the next segment in great detail. There's a certain amount of electrical testing and functional testing that goes forward here. Then it comes out of acceptance testing and you're ready to energize it. So you've done your electrical testing, you do your final test, you've phased everything, you've tested everything, hopefully with full voltage, and you connect it to the load and you start to conduct power, and it starts to do work, actually, is what that's called. When that energy is passed through the breaker, it's actually called work. So you start to do equipment. work and that enter service. And when that happens, you start this first 5-year maintenance cycle. So operational switching begins. It starts to watch for faults and overloads. Then you've got a 1 to 5 year maintenance period. Please don't go beyond 5 years with that initial maintenance period. But there again, is it 1, 2, 3, 4, 5, 6, 7? What is it? Depends upon your requirements. It depends upon the criticality of the circuit. It depends on the condition of the atmosphere that it's in. Is it in a clean, pressurized room, a long ways from the ocean at sea level? It's kept at ISO. It's distribution gear. It's very seldom opened or closed. Probably 5 years is okay. If it's in a dirty environment, it's being used, it's a very critical breaker, a very critical circuit. It's in an environment near the ocean. It's in an environment near a chloride or something that produces chlorides. It's in a dirty environment. You probably want to increase that maintenance cycle. Breakers don't like to be fully loaded, unloaded, fully loaded, unloaded. That creates a lot of thermal issues, a lot of condensate and things. Steady state, low loading breakers survive much better. So all that has to be considered in this. A lot of people use the run to fail method. We're not going to test it until it fails. A lot of people use condition-based maintenance, and we're going to talk about all those techniques in the next sessions. So now you're running around this circle for 5 years. We're picking 5 years. At some point in there, as long as there's not a problem, it's pretty much trouble-free. It's fire and forget, okay? And you're on to other things. It's doing its job. It's conducting the electricity. The lights are on. The plant's operating. Everybody's happy. In comes the first 5 year maintenance cycle. So at some point, you're going to stop going around this 5 year maintenance cycle racetrack, and you're going to pull over to the side and you're going to do some maintenance. When you do here, you're going to take it offline. You're going to do some clean lubing and adjusting, we hope. You're going to do some inspections, some electrical tests, some mechanical tests. And there's 2 paths here. There's the path to red tag, and there's the path right back onto the race course, okay? So when you do this testing, if, for instance, you have no problems and you encounter no issues and there are no red tags or no issues come out of the test, it goes right back into service. And you continue to do this 5, 10, 15, 20. At this point, this equipment could be up to 25 years old. And it's going right back onto course every 5 years. You had very few problems. When you've had a problem, we call it red tag. Some people actually use a red tag. And that's a situation to where the breaker needs to go out to a repair shop, or you need to have someone come in and look at it, whether it's the original manufacturer or qualified repair service. That's your choice. Depends upon what's available to you, what relationships you have, and did you come out of this feeling good about the original manufacturer's service team. Now, every time it goes back onto the racetrack and does 5 more years, it comes back around, and after the first 25 years, it's then decision time. Do I do any mechanical maintenance? Do I do any repair? What do I do? Do I do any replacement? It's been in service 25 years. After 25 years, its original manufacturer's specified life cycle is there, but the equipment's in fine shape. It can be just like new. It can be used many more years, even though it's 25 years old. After the first 25 years, we're going to go to the operational secondary cycle. So now your equipment has lived a good full 25-year life cycle. It's been shut down, cleaned, lubed, tested electrically and mechanically at least 4 or 5 times. You've found some deficiencies. You've found some issues. You've uncovered everything that was not caught in manufacturing or in acceptance testing, because you'll catch some things. There's some things you won't catch in acceptance testing that you'll catch in these 5-year checks. And there again, I'm not telling you to use 5 years. I'm just picking that as a cycle to use in this presentation. You have to determine that yourself based on the conditions involved. So now you're going to go back into this racetrack, and you're going to run it around the track 4 or 5 more times for 25 more years. Now, somewhere in here, the people that originally specified the equipment, the people that originally did the acceptance testing are going to retire, move jobs, are going to be gone. And that's an important factor because now new people are going to come in. There's going to be a new maintenance manager, the maintenance electricians, the people that were actually trained by the original manufacturers will either retire or move jobs. So it's important that you have some training, some familiarity. Someone knows where the spare parts are. Someone knows where the manuals are. Someone knows where the drawings are. Someone knows what modifications have been made to that switchgear in its first life cycle. When you go into switchgear and you see everything is beautiful gray SIS switchboard wire, and there's two bright blue wires and a yellow one, kind of halfway loomed in, running down there and plugging in, that's when you need to think something's been modified here. Quite often the drawings aren't modified. It's Joe from electrical maintenance came down and ran that circuit because they had a problem. So that intelligence, that information needs to change hands when these people change hands. So you need to do some debriefing, and that's tough to get done. So be careful here because you have spare parts, you have maintenance tools, you have specific test equipment that came with the switchgear, you have transport trucks and lift trucks and things that came with the switchgear, you have spares, you have all these things for the switchgear. And if that intelligence, if that information doesn't pass down from one generation of maintenance crew to the next, you lose a lot of the utility of your switchgear. You'll end up buying equipment parts and things you already have at a later date. So in the next life cycle, you're going to go right back into the secondary life cycle so that you're going to run it again for 25 years. It's hard to sit here and even for me and talk straight for an hour. So in the second life cycle, okay, you're going to do the same thing again. The difference is going to be the output, because when you output in 25 years, the equipment's now going to be 50 years old. And there's a substantial difference in 50-year-old equipment and 25-year-old equipment. The usage, the number of operations, and the condition of the equipment is substantially different. So when we go through it the next time, we have to talk about some possible minor life extensions, possibly breaker overhauls at the between 25 and 50 years. Possibly there's some control upgrades, new relaying, new control transformers, CTs, PTs, things that you want to do. Maybe you want to upgrade or retrofill the overcurrent protective devices, change some of that sort of thing. So between the first and second life cycle, there is some minor life extension things you may want to consider. And there again, the paper deals with that, and we'll talk about that in detail later. Just believe me, there are. The equipment goes back into service, and you see these 5-year cycles again, by which you do similar testing, similar inspections every 3 to 5 years for the next 25 years. So in these, you continue to catch now the degradation. So now you start to catch things are degrading. You'll find through acoustic or PD, you will find some insulation breakdowns. You will find some operation issues. For instance, these vacuum breakers have wear limits. So they have to be maintained at a certain wear limits, and each vacuum interrupter has a different wear limit. Also, they'll operate pretty well up to about 1,000 operations. Beyond 1,000 operations, you start to get wear out mechanically. Now, a lot of people say 1,000 operations. My breakers see 200 or 300 operations a year, or 20 operations a year, or 1 operation a year. There are a lot of equipment, a lot of breakers out there that are in repetitive application duty that see thousands of operations a year. And sometimes at about 3,000, the mechanisms are pretty much in a condition to where they have to have major maintenance. We'll get to that in the next cycle here.
Hey, Finley.
Yeah.
Yeah, I just want to point out when you just crossed your arms there, it got a little bit muffled. If you can check that mic and make sure it's not blocking your voice there. Thank you.
Okay. Sorry, guys. Yeah, I've got a little microphone doohickey right here, and I don't bring it all the way up here because then you can hear me breathe. I'm a bad breather. I guess I don't remember where we were at, but we're coming out of the second life cycle. Now we're talking about maintenance after the equipment is 30, 40, 50 years old. So at that point, you start to see some red tag operations for wear because the breakers are wearing. you start to see some situations to where they have a lot of operations on them. Generally, it's generally accepted that these breakers have sealed bearings and they were designed to operate some period of time with very little maintenance. Is that 20? Is that 25 years? Is it 50 years? Everybody has a different opinion. But everything has a bathtub failure curve. These breakers do too. When they're young, a lot of them fail. After they go into service a few years, they maintain a very good, robust lifetime. And then at some point, they start to fail again. That period where they start to wear out is usually conceived around the wear limits of the circuit breaker. The contacts are doing this. The contacts are changing. The contacts are wearing. At a certain point, the wipe springs, which this paper does a very good job discussing, the wipe springs are there to hold pressure on the interrupters to stop popping forces from damaging the breaker if you see an overload. At a certain point, those wipe springs can no longer maintain the proper pressure on the interrupter, and they will possibly damage themselves if they're called upon to operate in an overload situation. Or possibly they will not interrupt a full, they always say bolted fault. You never see a bolted fault. Very seldom do you see a full bolted fault. So at about 1,000 operations, you need to do some pretty significant maintenance. At about 3,000 operations, in my opinion, most modern vacuum breakers need to be completely overhauled, and that's a complete mechanical overhaul with new coils, new charging motors, pawls, charging gears, springs, a lot of components. It's a fairly detailed that are replaced with a proper replacement breaker. And we'll get into that in the next segment. Now, after this next cycle, if you don't get a red tag and the equipment goes right back into service after 4 or 5 cycles, it's now 50 years old. You've done all the clean, lubing, inspect. You've done all the electrical and maintenance tests every 5 years. Now you've been through 10 of those maintenance cycles and the equipment's 50 years old. And we're coming up upon that period on a lot of equipment right now.
I have a couple questions here, Finley. Just real quick, I'll pop an answer out for you. Would we be able to send a copy of the presentation? And the answer is yes. We'll have a recording for this available. And then you mentioned about NETA and the paper. There are questions about where to access the paper later with follow-up sessions and conferences on this topic.
As soon as the NETA conference is over, we will have another session April 21st. At that point, we'll distribute this paper to every one of you.
I got one more for you there, Finley. As switchgear gets 50 plus years old, is there a concern that inaccessible areas such as line side bus could be experiencing age-related insulation degradation issues?
Yeah, we're going to get into that with the non-destructive and online testing techniques. And the line sign bus is absolutely sealed off. It's hard to get into. Most people's maintenance cycle doesn't give them enough time to get in there and inspect that properly and clean that. There's ways with partial discharge, there's IR, there's acoustics, there's all kinds of ways to look for corona discharge, to look for partial discharge, to look for that degradation without having to remove those panels. But like I said earlier, the best way to do it is open it up, put your human eyes on it, and look for the telltale signs of insulation erosion. And when we get into the MTS section, which is the 3rd installment on this series, we're going to talk in great detail about that. In the 4th installment, we're going to talk about non-destructive and online testing techniques that will help you to get to those problem areas without having to remove those panels. I don't suggest it. Certainly, if the equipment's been in service 50 years, 75 years, 100 years, I hope you've looked at every inch of it a few times. Probably at 100 years, you've already replaced the insulation that's in that compartment with something more modern. Okay, let me see where we're at. We better move forward here. So now we're leaving the operational secondary cycle. We're heading to the first life extension primary cycle. That's where we start to see some of the things we just mentioned, like insulation failures. And we're going to move forward. Now you see another cycle that looks similar to the last one, but there's a few changes. Now the equipment's 50 years old. And you're going to have to operate it from 50 to 75. Now we're peering into the future because the oldest of the current equipment is about 50 years old. So now we're talking about speculation. And for the next two segments, we're peering into Finley's magic ball. So what's going to happen in the next 50 years between now and 75? Well, most of the people on this call won't be in this business anymore. Most of the people on this call's kids will be in this business, but this equipment will still be in service because there is nothing today to replace it with. And replacing it with like kind equipment is very feasible in situations where you have plenty of room. You don't mind disturbing the cables and possibly having to replace the cable, or you're willing to put tap boxes in and jumper the cable over, which creates a whole nother myriad of problems. So a lot of the gear will just stay in service. So now it's time to do a real evaluation versus repair versus replacement. Now, the equipment that stays in service over this 25 years is probably going to stay in service another 25 years. The equipment that you replace now is equipment that's going to start its life cycle over again with modern equipment. That equipment might have more modern insulation, more modern controls, more modern breakers, but they won't be as robust as the ones you'll be getting rid of. Their actual life cycle will be less. The circuit breakers you get today, the vacuum interrupters you get today will not live as long as the ones that were created 30, 40, 50 years ago. So don't expect them to. The switchgear might, though, because insulation materials, controls, instrument transformers, some of that stuff has become more robust. The other thing that you might get to is you might get some arc resistant switchgear now that you didn't get in the last cycle. So in the last cycle, the equipment that you got, the last two cycles probably was not arc resistant. So you probably have to deal with PPE, with hot zones of arc flash zones, remote racking, remote switching, that sort of thing, where the new equipment that you get in the next 25 to 50 years might deal with that problem internally. It might have onboard racking. It might be arc protected. There might be all sorts of things designed into it. The problem is disturbing the cables. These cables are now 50 years old, and 50-year-old cables don't like to bend, don't like to move. So if you disturb the cables, the chances of damaging a cable is pretty great. That leaves you with having to possibly tap from that existing cable, leave the old switchgear in place, and tap jumper cable from it over to the new gear. Now you've got two more joints. Those joints are normally not shielded. It's normally jumper cable. So you have all kinds of long-term issues there. So we'll talk about that in the fourth segment and the properties of doing that. Let's forge forward.
Finley, along that line of accessories and other things other than the breaker, what about, and this is a question, what about the life of protection relays and trip units installed on the breaker?
Well, when we say right here, if you look on this next page, I just clicked to, every one says OCPD. That's the overcurrent protected devices. That's the relays. I know it says overcurrent, and a lot of these particular relays are voltage controlled, frequency controlled, differential schemes. There's all kinds of other situations in there. But basically, when I say OCPD retrofill, I'm talking about the controls, meaning any of the protective devices. So as you move forward, obviously, the original gear was primarily induction disc technology. So in the original installation 40, 50 years ago, a lot of these were induction disc. Then they went to analog electronics. Analog electronics has a subject to drift. So you've got resistors, capacitors, all sorts of things that drift. So a setting doesn't necessarily mean that setting anymore, and everything has to be calibrated and the settings have to be changed. From there, it went to microprocessor-based controls, which are not quite as subject to drift, but are subject to, more subject to transients and failure due to those sorts of things. So every version has its downfall. I would say the new modern microprocessor-based stuff is far more robust and far more reliable. It's not more repeatable than an induction disc relay. An induction disc relay is very repeatable, does a fine job, but is limited because of corrosive atmosphere, magnetic forces, dirt, dust, and really the people around to calibrate them and take care of them are mostly gone today. So really, the new relays, new transformers, the Hall effect sensors instead of CTs and so forth are very good options. Let's continue along. Let's get through the presentation. When we still have time for questions, then we'll come back and I'll circle back to any of these questions. Mike Sposato, I see you joined us. I was with your buddy Joe last week in Jersey. He sends hello to you and hope things are going well for you. You know, we do get into a situation here with, well, someone's trying to send me a text about one of y'all. Okay, so we do get into our major life inspection and major life extension situation here, where minor overhauls at about 1,000 operations, major overhauls at about 3,000 operations on the mechanism. And there again, we're talking about medium voltage vacuum breakers, medium voltage meaning 1,000 volts to 38,000 volts, mostly draw out breakers. So at the 3,000 operations, we'd like to see a major overhaul of the breakers. At 1,000 operations, we'd like to see some minor overhaul. At this point, you start to see some control upgrades, and I think that's what the last question was asking about, is at this point when the equipment's 50 to 75 years old, I think you'll see most of the controls are upgraded, control wiring, cell switches, CTs, PTs, transducers, a lot of that stuff updated to whatever the new tech is. You'll see a lot of IC upgrades because the interrupting currents will have gone up, the systems will have stiffened, and you'll see a lot of people wanting to increase their arc flash capability or increase the interrupting capability of the breaker. And we're going to talk about that in segment 4. At this point, you really have to evaluate the criticality and the condition of your equipment to determine what you do. You might want to add some online testing, thermal PD or data logging capabilities if you don't have it. And you want to completely evaluate your insulating system and the control transformers in your system. And that's coming up. That's in the next 25 years. If your equipment's 40 or 50 years old, these are the things you should be looking for and planning for right now. It goes back into service, and here you go again on this racetrack. Every 5 years, you're going to test it. So now it's 55 years, 60 years, 65, 70, and 75 years. You're going to do the same maintenance test, inspect, clean, lube, and adjust on these mechanisms. You're going to do a lot of timing tests that you didn't do on the early sections in the later years to ensure your breakers are operating at speed and velocity. And you're going to make sure you change that lube because they don't like staying closed like this for 50 years, right? There again, the same thing happens. The ones that fail go to red tag. They go out for repair, replace. It's decision time on this old equipment. The things that pass test and inspect are going to go right back on the racetrack 5, 10, 15, 20, 25 more years. And then you're going to move on to your secondary life extension or your 75 to 100 year cycle. Now, 100 years we thought was a long time, but here we are, we're there. Even more major life extension, major breaker overhauls. We're replacing controls. We're retrofilling them with new breakers. We're installing new breakers in the place of the old ones. We're keeping the switchgear so we don't have to disturb the cables. We're completely replacing the breaker elements. We're upgrading the IC. We're evaluating the installation. We're evaluating control transformers and replacing transformers. We're finding a lot of insulation breakdown and insulators and different types of insulation. And a lot of that can be picked up pretty easily with online techniques and non-destructive testing. It goes in for another 5, 10, 15, 25. It comes out now, it's 100 years old. The stuff that didn't red tag goes right back in and it's lived to be 100 years old. You know, at any point in here, there's these decisions you have to make. Do I repair? Do I service? Do I lubricate and keep my equipment in service and extend its life? Those techniques are available to us. Or do we scrap the equipment and replace it with new? That's really the decision you have to make. And that's the decision that has to be made, I would say, every 25 years. The problem with scrapping it is disturbing the cables. Can you get in there? Can you get in the place to replace it with new equipment? Have you built around it to the point to where you don't have good access any longer? when a lot of these switchgear rooms are built, there's a nice big roll-up door on the end, but now maybe outside that door, there's been a buildup. Maybe the door's been replaced with a block wall over years. There's a big heater there. There's a big furnace there, whatever. 50, 60, 70 years ago, all that was considered, but now you've built up around the gear and it's tough to get out. The key takeaway should be is you can't test in reliability in these systems. You have to earn that reliability. You do that by doing these maintenance issues, by doing these inspections. We've just done 25 scheduled 5-year maintenance cycles in this gear to get to 100 years. You've earned reliability because you've done the work. You cannot simply say, hey, I'm going to test it and that's going to make it more reliable. You have to test it on a reliable system, on a reliable schedule, and then you have to cycle it through repair and upgrades, and you have to think about all these upgrades and life extension techniques as you go along. You must remain observant and diligent with plans and upkeep to earn the reliability in your electrical system. Don't expect it to be reliable. Don't expect it to survive to 100 years. You have to earn that by actually doing the work. That gets us to 100 years. Our equipment's now going to live for 100 years. Everybody on this webinar now has some things to think about. And over the next 3 segments, we'll dive into these with more detail, segment by segment by segment. It's a 4-hour course. I'll be conducting the entire course at NETA next month, and I hope to see some of you there. Any questions?
Yeah, you know, one thing that struck me as you were talking, when a cable remains undisturbed, what kind of life cycle do you anticipate with that, the cabling there, assuming it's never actually touched or moved?
Depends upon the type of cable. Some of the early cables that were installed, for instance, at 20 or 25 years, you don't want to disturb them at all. Some of the armored cable you can disturb. You have termination issues. There again, when you start to disturb cables, you're working in the twilight zone. And the guys here that are cable guys understand what I'm talking about. If you disturb and damage a cable, you're talking hundreds of thousands of dollars to replace the cable and weeks of downtime. So the people on this call, the last thing they want to do is go to their customer and say, hey, we've got to replace this 1.2 miles of armor-clad cable that runs through 7 manholes. You know, so the cable becomes just as big an issue as the switchgear, and sometimes even more. And I've been involved in many of these cable renovation projects over the years, and they can become very sticky.
Yeah. So let's jump into a couple of questions and comments here. Let's see. What about CTs that are installed on the line side of the switchgear main bus?
Well, if they're on the line side, they're tough to get to. You have to take a complete shutdown to get to them, and you have to remove a lot of bus to get to them. Sometimes it's easier to go through the switchgear cubicle than it is to go through the busway to get to them. There again, these current transformers are designed for very long life. You see a lot of them that weep epoxy. You see a lot of them that start to essentially melt and come and separate and crack. So you see a lot of degradation in current transformers. And quite often people use low voltage transformers and an air gap. Quite often they use medium voltage transformers that are direct contact transformers. It kind of depends on the application. This is real site specific stuff. And if I don't know really what you're dealing with, it's hard for me to recommend to you what to do. But a good visual inspection, keep them clean, look for cracks, do an acoustic test, do PD testing, do the sorts of things to tell you that there's no breakdown, no corona effect right now. What PD does, PD is a capacitive discharge that's constantly damaging the insulation. Once it trees, it becomes kind of a corona discharge. Then you get acids and you get the treeing effect and the things that you visually see. Once you get to corona, you can pick it up with acoustics. You've normally got a few years before failure at that point. So make sure you do a good acoustic study, you do a good PD study of your medium voltage systems. If it's encased in a steel busway, it's harder to get to, no doubt about it. But you do have these shutdowns every 5 years. Maybe you go in and look at a piece of your gear on one section, you look at another piece in 5 years, you look at another piece in 5 years. You know, don't wait to the 50-year mark to start looking at that equipment.
Tim Conley says there are limitations associated with partial discharge evaluations because of equipment design, operating voltage, and other limitations.
Sure, absolutely. The lower the voltage, the less effect you'll have with PD. If it's encased in steel, then you've got to look at TEV, transient earth voltage detection, instead of radio frequency. So it's a toolkit, guys. You're lucky that you have a big toolkit today. There's all kinds of tools available that work. And Tim, I know you know what you're talking about. Tim and I worked together for many years. You know, he knows these PD systems. There are situations to where with RF, you can get into a room and detect PD and triangulate where it's at. There's TEV sensors where you can work around the switchgear and kind of point down to where the problem is. There's acoustics. You can't underestimate the power of acoustics. But when the discharge is enclosed in a metal case with no louvers or no air ventilation, then you can't hear the noise. So there are all kinds of techniques to use. When we started this presentation, I said, your eyes are your best weapon. So your best weapon is to get the panels off, get in there and look at the tape, look at the insulation, look at the CDs, clean them, do an inspection. And the problem is you have to be prepared for what you find. And Tim knows what I'm talking about, because you get into these places, you go look, and if you actually find something and you're on an 8-hour shutdown, now you're going to have to come tell your boss this is going to take a week to fix. So be ready for what you find, guys.
Another question here, Finley, is there a source of reliability lifecycle data that end users can refer to for lifecycle replacement justification, specifically for low voltage trip units, when they're looking at 20 plus years of service and the OEM is so far not providing an end of life statement?
There are a lot of people that have presented technical papers at NETA and at Pearl and at some of these locations on low voltage breaker retrofits. There's one in particular I can remember that I think Tony Di Maria presented. If someone will get to me offline, I'll try to go back through my records and dig that up for you. There's my email address and phone numbers on the screen right now. Send me an email. Don't expect a reply today, but I'll go back and see if I can find us a particular paper I'm thinking about that may be of benefit to you. It would be in the archives from NETA about 4, 5, 6 years ago.
You know, we are here for all your needed now electrical needs for both low and medium voltage breakers, and talking service, also transformers, vacuum bottles, replacement parts, circuit breaker safety devices from CBS ArcSafe, you know, just a whole supply of things that you need for your electrical needs. So, you know, let us know. Contact us at Group CBS. Thank you for logging in today. Finley, anything else, sir?
Anything you've got, let me know, guys. I'd be glad to help you. He had to get that plug in there. He's kind of a sales guy. I'm not a sales guy. Talk to you later. Thank you very much.
Thank you. Thanks, everybody.